Hey everybody, welcome back to Ivy Tutoring's ACT prep course. Once again, my name is Caden, and today we're going to be going through lesson 4 of the 10-part series. So if you're watching this, most likely you've completed the first 3 videos, right? If you remember in the last video, we talked a lot about the English exam. We went through some English exam questions and passages, and hopefully you've been reviewing those in the meantime between the last video and this one. Um, but let's get right into today's video talking about what it's going to be. So today's video, math topics, we're moving into the second section of the ACT exam, the second required section of the ACT exam, which is math, right? A lot of students struggle with math, albeit it's probably the hardest individual subject to improve on, just because there's such a broad array of content, right? Unlike reading or English, you can't really master the test when it comes to math and get a good score, right? You need to understand the underlying mathematical concepts that underlie questions on the ACT. Right? That being said, there are some strategic tips and tricks that the ACT likes to pull on the math exams, which we talked about briefly in lesson 1. So if you want a little bit of a reminder of those before doing some practice, definitely go back and check that video out, right? But today's video is going to be specifically focusing on here there 5 of the most difficult, or usually like the most difficult questions for students on the ACT, right? Obviously, in 1 hour, we're not going to be able to cover all of Algebra 1, all of Algebra 2, trigonometry, pre-algebra, geometry, pre-calculus, right? There's no way we can cover all of that information, right? We can't even give a brief synopsis of that in 1 hour, right? What I've decided to do with today's video is essentially take the 5 most important, like concepts that I see students get wrong the most, right? That schools tend to not place a lot of emphasis on, right? School systems, and therefore students come into the ACT unprepared. So basically, the idea is if you have a score, you're sitting around a score anywhere below about 30 to 32, right? So you're anywhere below that between 10 and 28 to 30, right? Anywhere in that range, it's very likely that one of these 5, if not more, concepts you keep getting wrong on the questions, right? Because these are kind of the sneaky topics that you need to understand that help you in lots of different types of questions, right? Not just one specific format, right? They show up over and over again. So the goal of today's video is I'm going to give a brief discussion about what these topics are and how to approach questions related to them, right? And then in the next video, lesson 5 is going to be the second part of the math, topic section. What we're going to be doing in that video is going through an actual math exam, just like we did with the previous exam, with the English exam, right? We're going to be going through a math exam, and I'm going to be solving math questions and explaining to you how I'm thinking about them and how you should be thinking about them. Okay, so that's for our next video. But for today's video, let's jump right into it. The first, major topic that we want to discuss is GCF, LCM, and square roots. Okay, so let's talk about GCF and LCM. So first of all, what are GCF and LCM? GCF is greatest common factor, greatest common factor. Okay, and LCM is least common multiple. That's what these, acronyms stand for. And they're useful in a lot of different ways. But let's talk about what each of these things actually mean. Right? For greatest common factor, the greatest common factor, well, what is a factor, first of all? Let's say we have some number, say the number 12. The factors of 12 are any number that goes evenly into 12. Right? Basically, any 2 whole numbers that multiply together to give 12 are both factors of 12. For example, the numbers 2 and 6 are factors of 12, right? Because 2 times 6 is 12, right? The numbers 1 and 12 are factors of 12 because 1 times 12 is 12, right? And the numbers 3 and 4 are both also factors of 12, right? So 12 has 6 factors. It has the factors 1, 2, 3, 4, 6, and 12. Okay, so one thing that you should notice is that all whole numbers, right, all whole numbers will have factors 1 and themselves, right? So what we call those, numbers, like the number 7, where the only two factors of the number are 1 and itself, right? No other two whole numbers multiply to be 7. We call these prime numbers. Okay, so prime numbers are very useful, and we'll talk about them a little bit later when it comes to factoring. But basically, primes are, the base factors of all numbers, right? There's a proof in math that says all numbers or all whole numbers can be broken up into a set of all primes multiplied by each other. So basically, uh, every number is just a multiplication of multiple primes. For example, um, any number greater than 1, I should say. Like the number 60, or we'll do a simpler one. The number 12 is just 2 times 2 times 3. All of these numbers are prime. If you multiply them together, you get 12. Now, knowing that is not super important, but knowing how to apply it is. So now we know what a prime number is, and the factors of a number, we know what that is. Now, what is the greatest common factor? Well, what it means is you have a set of some numbers, right? Usually it's 2 or 3 numbers. Let's just use 2, for example. The number 12 and the number 20. If we want to find the GCF, the greatest common factor of 12 and 20, what we're looking for is, well, pretty self-explanatory, the largest of the factors of the numbers 12 and 20, right? So the factors of 12 are 1, 2, 3, 4, 6, and 12. And the factors of 20 are 1, 2, 4, 5, 10, and 20. Now, with these small numbers, we can do this pretty easily, right? We can think of the factors because there are not that many of them, right? 12, 20, pretty small numbers. So what are the numbers that are, what's the largest of these numbers that is shared between the two lists? Well, it's not 20, it's not 10, it's not 12, it's not 6, it's not 5. Oh, there it is, 4. 4 is the largest common factor, the greatest common factor between these two numbers, right? So we could say, the GCF of 12 and 20 is 4. So if we're using this, that's super helpful, right? We always like GCF, right? It's used in a lot of different applications. A lot of the time, it just asks us directly for the GCF of two numbers, right? Now, let's say we're using more complicated numbers. For example, let's say the GCF of 24 and 156. Okay. How do we do this one, right? So there's a couple of different ways we can think about this, right? Basically, we're looking for the largest number that is a factor of both 24 and 156. Now, let's say we don't just write out the factors, right? Maybe we're using bigger numbers, right? Here, we could probably write out the factors as well, but we're just going to do it as an example, right? To find the greatest common factor of two numbers, like this, okay? The systematic way is to break each number into its prime factors. Basically, all of the prime numbers that multiply to give us the total value. How do we do that? We're going to do a tree technique. Here's what I mean. Start with one of the two numbers, 24, for example. Okay, break the 24 into any two factors, any two numbers that multiply to be 24. You don't want to use 1 and 24 because that won't really be helpful. But for example, let's use 2 and 12. Okay, well, 2 is a prime number. So we circle it, right? 2 can't be broken down any further. It's just going to be 1 and 2, 1 and 2 over and over again, right? So we circle the prime number, and we keep going with the 12. 12 is 2 and 6. 6 is 2 and 3. So what we've now done is we've broken 24 into 4 prime numbers, right? 24 is the same as 2 times 2 times 2 times 3. Okay, so that's 24. So we've given it its prime factorization. So this is a prime factorization of 24. So let's do that same thing with the number 156, right? The other number. You get 2 and 78. 2 is prime, so we just keep going with 78. 78 is 2 and 39, which is 3 and 13. And those are all prime numbers. Okay, so these are prime numbers. Okay. So what is the prime factorization of 156? We'd say 156 is 2 times 2 times 3 times 13. And now here's the magic, right? How do we find the greatest common factor of these two numbers, 24 and 36? What we do is we look down here, we investigate these, uh, you know, prime factorizations, and we basically find all of the things that are the same between them. For example, there's a pair of twos that are shared. There's another two that is shared, right? There's also a three that is shared, right? So these are shared prime factors. And what we do is we take these shared prime factors, a 2, and a 3, and if we want to find the GCF, GCF is just going to be these shared prime factors multiplied by each other. 2 times 2 times 3 is 12. And so our GCF of 24 and 156 is 12. Okay, so the technique to find a GCF is very simple, right? You take the two numbers, you break them into their prime factors, and then you multiply the shared prime factors together, right? You see whatever is shared between the two numbers, okay? And you multiply them together. So that's GCF. Now, what about LCM? What about LCM? Now, LCM is very useful because LCM's, least common multiples, let's talk about what a least common multiple is first. Least common multiple is between two numbers, say, um, you know, 6 and 9. What is the smallest number that is a multiple of both 6 and 9? Remember, multiples are numbers where you take the original number, the base number, like 6, and multiply it by any whole number. That's called a multiple of 6. For example, the multiples of 6 are 6, 12, 18, 24, 30, and so on, forever. Right? And the multiples of 9 would be 9, 18, 27, 36, 45, and so on. And we're looking for the least common multiple, so the lowest number that is shared between these two lists of multiples, and that's just going to be 18. We can see that very quickly, right? With small numbers, it's easy to see. Okay, but what about large numbers? What if we want to do least common multiple of, for example, 24 and 156? Let's stick with these same numbers. The great thing is the technique at the start is exactly the same, right? So you just prime factorize the two numbers. So let's prime factorize. We already did it. So 24 is 2 times 2 times 2 times 3. And 156 is 2 times 2 times 3 times 13. Okay, so these are the prime factors of 24 and 156. Okay, and the way we find an LCM is by finding the shared pairs, right? We're going to find the shared pairs, 2, 2, and 3, just like we did with GCF. And we're going to multiply those together, just like we did with GCF. So we're going to do 2 times 2 times 3. Okay? But the last thing that we have to do is we also multiply by the things that aren't shared. So we're going to multiply by this 2 and this 13. So we're going to take this number, the number that we got from the red, the shared pairs, multiply it by the outcast 2 and by the outcast 13. What that's going to give us is 12 times 2 times 13, which is 24 times 13, which is going to be 312. So the least common multiple of 24 and 156 is 312. Okay, so this exact same technique, right? Prime factorize, find the shared pieces, is used for GCF and LCM. The only difference is for LCM, you also multiply by the non-shared pieces. Okay, so those are the two differences. Why might LCM be useful, right? Why might it be useful to figure out the least common multiple of two numbers? Well, imagine you have fractions, for example, right? Imagine you have the fractions, um, you know, 3 over, no, we'll do 1 over 12 plus, no, we'll do 1 over 24 because those are the numbers we're using. 1 over 24 plus 1 over 156. Now, if you wanted to add these two fractions up together, what you would do is get a common denominator by finding the least common multiple of the denominators. What we just did was found out 312 was the least common multiple, right? And then we convert 24 1/24 into 312ths. We do 312 divided by 24. What we get is 13. Okay, so we get this number becomes 13 over 312. Okay, and this number becomes 2 over 312. Okay, so we can add 13 plus 2, and you get 15 over 312 as our answer. Okay, and we can simplify this further if possible, right? You'll divide by a 3, for example, get 5 divided by 104, and that's going to be our final answer. Okay, but you needed to figure out the least common multiple of 156 and 24 in order to combine the two fractions, right? So the LCM is commonly used in fraction addition, right? That's probably the biggest thing that you'll see on your ACT, where LCM are used. Okay. Now, I did promise that we were also going to talk about square roots, right? We don't want to spend too much on this, but really briefly, LCM, GCF plus LCM, the last thing we have to talk about is square roots inside of this topic, topic 1, square roots. And for square roots, basically, the thing I'm getting at here is how do you simplify? So if some question asks you, these show up a lot. Simplify square root of 108. How would you do it? Okay, we don't know the square root of 108. It's not a whole number, but how do we simplify it? Well, what the ACT wants you to do is break it into its smallest possible square root times some whole number on the outside, right? Some whole number here and some square root number on the inside. How do we do that? Well, we're going to do the same prime factorization technique we did for GCF and LCM. We're going to take 108, we're going to split it into its factors. 2 and 54, 2 and 27, 3 and 9, 3 and 3. So we're left with 2, 2, 3, 3, 3. So 108 is equal to, we could say this, the square root of 2 times 2 times 2 times 3 times 3. Right? All I did was I broke 108 into something equivalent to it, 2 times 2 times 2 times 3 times 3. And we also know that this is equal to the square root of, look at these pairs, 2 times 2 and 3 times 3. So that's equivalent to 2 squared times 3 squared times 2. Okay, and 2 squared times 3 squared is just 6 squared. 6 squared times 2. So now what we've done, well, what's the square root of 6 squared? Well, it just cancels, right? So this is equal to the square root of 6 squared times the square root of 2. And the square root of 6 squared, like we said, is just 6. So it's just going to be 6 times the square root of 2. Okay, so now we've simplified the square root of 108 into something much simpler, 6 times the square root of 2. So just to review that, the technique we did was we found the prime factors, okay, found the pairs, found all the pairs, combined the pairs into one square. So instead of 2 squared times 3 squared, we got 6 squared, right? And then the square root of 6 squared is just 6. So we can bring that right to the outside as a whole number. Okay, we're just left with the stuff that wasn't paired up. Okay, so this same kind of technique is very common. It shows up in square roots, shows up in least common multiples, greatest common factors, right? Prime factorization is a huge part of the ACT. So it's very important to know what it is and how to use it, right? So make sure you follow along there. I should also preface this video or add to this video that if you do have, more questions about things on this topic or on other topics, right? One of the Ivy resources that I find super helpful for a lot of students is the Ultimate Guide to the ACT Math section. That's in our Ivy Tutoring Resources section inside the Math tab. Go check it out. It's a big textbook, right? So it's like 380 pages or something like that. So I wouldn't say go over and read the whole thing, right? That's kind of going to be a waste of your time. What I would do, though, is spot check a couple of questions in each, category, and then go see, okay, do I know how to do this question? Yes? Okay, I've got that section down. I don't have to review it. But go spot check and try doing questions over and over. And if you find things that you don't really know how to do, then go read the 3 to 4 page, monologue by the author on how to answer questions like this. Okay. Obviously, in an hour, I'm not going to be able to cover all of the stuff in that textbook, but it's available to you. Go take the time, practice it out. Okay. So yeah, that's GCF, LCM, and square roots, right? The next thing we want to talk about is counting and probability. Oops. We'll go counting and probability. So counting and probability. And this might seem, simple to some people, not super simple to others, right? Counting might sound pretty simple, but let's talk about what we mean by, counting. Like, why is counting actually important? So there's a couple of things that we have to talk about. First is permutations and combinations. Now those sound like big words, but let's think of a question. Let me pull up a question real quick. Let's say you have four books. I have four books colored red, blue, green, and yellow, and I want to put them on my bookshelf. Okay, so I'm putting them on my bookshelf. How many different ways can I arrange them on my bookshelf? That's question one. How many ways to arrange, right? Well, let's think about this. We have, okay, on this bookshelf, this is a better example. On bookshelf, we have four possible slots to put each book in. And let's say we go left to right, right? How many different choices do we have for our first slot? We have four. Okay, how many different choices do we have for our second slot? It's no longer four because we already put one into our first slot. Once we slide, say, the red book into the first slot, we don't have the red book to put in the second slot now. So we only have three left. Then we have two left, and then just one for our final slot. Right? So what we've done is this is the number of choices we have per slot. Right? And if you think about it, that means we're going to have 4 times 3 times 2 times 1 choices for the total arrangement, which is going to give us 24 total arrangements. Okay? 24 total arrangements. Okay? So essentially, this is kind of how to arrange to a set of, figurines or whatever. This is what happens when the order matters. Okay. Now let's talk about a little bit of a simpler example or another example that shows up a lot. Let's say there are 10 students in a class, and the teacher is going to select 2 students. Well, actually, let's do this. The teacher is going to select 3 students for honor roll. So 3 students are going to get selected for honor roll. Okay. How many combinations of students can possibly be selected for honor roll? If the teacher is just picking them at random or making a conscious decision, but either way, they still have to pick 3. The teacher has to pick 3. How many different sets of 3 students can be picked? Now, here's my question. Okay. Well, how many students can you pick for the first slot? Well, there's 10 students for the first slot, just like we did with the books, right? 10 students for the first slot. Okay. Well, how many students are there for the second slot? 9. And then 8 students for the third slot. That gives me a total of 720 possible combinations. But wait, let's imagine I pick student A, B, and C in that order. I picked A first, and then B, and then C. Okay. Is that different than me as the teacher picking B, and then C, and then A? Right? Because in our permutations, right, that's a different combination, right? We picked a different number for this one, or a different student for this one, a different student for this one, a different student for this one. So definitely not the same, one of the 720 permutations. But we're looking for any combination, right? Where the order doesn't matter, right? The order we pick these students doesn't matter because all of them are getting honor roll, whether the first in the order that we picked them or third, right? So these combinations are the same, meaning we double counted this combination. Right? But we did more than double count this combination. CBA is also the same, or BAC. All of these are valid examples that we counted in this permutation that we figured out, right? We counted them, but we shouldn't be counting them in our overall question, asking how many different combinations of students work. Okay, so the real question you have to ask yourself on questions like this, where you're picking students or picking things out of a jar or whatever, right? The question you have to ask yourself is, does the order in which we pick these students matter, right? And if so, there's a specific way to figure it out, right? If the order does matter, all you have to do is take 10 times 9 times 8, or figure out how many choices there are for here, here, and here. Right? Because if order matters, we're picking the top 3 students staying in the class. We're picking first place, second place, and third place. Then ABC is different than BAC. because they have assigned spots, right? But if we're just picking three students, for honor roll, and all three students get the same, value at honor roll, right? It doesn't matter what order you pick the students in, right? So if you wanted to say how many different ways can we label them first, second, and third, the answer is 720. But if we wanted to figure out how many ways can we pick them for the honor roll, here's what we have to do. You take that 10 times 9 times 8, and what you do is you divide it by the possible orders of the three students that you pick, right? So what you do is you take the students that you've picked, three possible choices for the first order, two possible choices for the second one, and one remaining, just like we did with the books, just like we did with the students, right? Say you have A, B, and C, we know they're going in honor roll. Now you have to figure out the order they could have been chosen. There's three possible choices for this, two possible choices for this, one for this. So we divide this 10 times 9 times 8 number divided by the possible orders that we overcounted. So what we see here is we get 720 divided by 6, because every single combination we counted in the 720 had 6 equal combinations. Basically, ABC can be written in 6 different ways. ABC, ACB, BAC, BCA, CAB, CBA. So every set of 3 students we picked, right, has 6 equal combinations, right? So we have to divide this double counting, not double counting, sextuple counting, because we 6 times repeated, right? So we divide 720 by 6, and that gives us 120 honor rolls, I guess, right? 120 distinct honor rolls that the teacher could give out. Okay? So the real, hopefully you're able to see this kind of in action here. The difference between picking a combination, which is this one over here, combination, and a permutation, is whether or not order matters when choosing the values. Okay? Does the order matter for where the students are being picked? If so, then we have to all we have to do is take 10 times 9 times 8. Imagine they're getting placed in first, then second, then third place. If the order then the order would matter, right? So we just do 10 times 9 times 8. If the order doesn't matter, and we're just picking a group of 3 students, you have to take 10 times 9 times 8 and then divide by the orders that you double counted, right? Your counting order, when you just take 10 times 9 times 8, to get rid of that inclusion of order, you divide by 6, or divide by the number of students that you've chosen times, technically the number of students you've chosen factorial, right? You chose 3 students, you take a factorial. If you've never seen what a factorial is, it's very simple. Factorial, the exclamation mark means factorial, which just means multiply 3 times 2 times 1. Factorial of 7 is just 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so don't get hung up on that. You won't really see that on the ACT, but it's useful to understand for permutations and combinations. Right? So that's kind of one of the biggest things in counting that's very important. And then the next thing is probability. Okay, so a lot of students oftentimes get tripped up on when to multiply, when to add, things like that. Right? So here's the question. Let's say tomorrow there is a 30% chance of rain and a 10% chance of lightning. Okay, here's my question. What are the chances? What's the probability that it both rains and lightnings tomorrow? Or there is rain and lightning tomorrow? Okay, so the weather forecast tells us there's a 30% chance of rain and a 10% chance of lightning. Okay, here's how you do it. You take, okay, what are the odds you get rain? Just think about the first condition, right? We have to break this into 2 conditions, rain and lightning, separate conditions. Okay, what are the odds there's rain? Well, it's 30%, so 0.3, or 3 in 10. Okay, those are the odds that there's rain. What are the odds that there's lightning, right? What is the chance that there's lightning? Well, there's 0.1 or 1 in 10. Okay, So let's say we took 100 days, right? 100 days. Okay. Basically, what's happening is 30 of those days that it will rain, and 10 of those days it will lightning, right? Now, the odds of these days overlapping, assuming that these two things are not related in any way, let's assume that rain and lightning are not related. This might not have been the best example for that, but let's assume they're not related, okay? Um, the way to figure out the odds that both of them happen, you take the odds that one of them happens and you multiply it by the odds the other one happens. This might not seem super intuitive, but let's think about it. The other thing that students a lot of the time do, and this would give you 3 out of 100. So you'd expect 3 out of 100 days it both rains and lightnings on the same day. Okay, let's think about what would happen if we added these two together. Well, that gives us 4 out of 10. Okay, so that means that's 40% of the days. Okay, that doesn't make much sense, right? Because what are the odds it rains and lightnings? Well, if the odds of that were 40%, that means it better rain at least 40 days. And it better also lightning at least 40 days. But that doesn't make sense. We know it rains only 30 of those days, 30% of the time. And we know there's lightning only 10% of the time, right? So adding these two up doesn't really make much sense. The reason that we multiply is kind of like once we have the first thing happen, right? There's 4 possible outcomes, right? No rain, no lightning. Okay. Then there's no rain, yes lightning. Then there's yes rain, no lightning, and then yes rain, yes lightning. And this is the one that we care about. We want that one, right? So no rain, no lightning. Well, what are the chances of that? Let's think about it, right? No rain happens 7 out of 10 times, 70%, right? And no lightning occurs 90% of the time, right? So of these 7 out of 10, right, we should get 9 out of, so these two, I should say, are 7 out of 10, right? These two together are 7 out of 10. 7 out of 10. And these two together are 3 out of 10 because that's just dependent on the no rain happens 7 out of 10 times. And then no lightning should happen of the 7 out of 10, it should happen 9 out of 10 additional times and 1 out of 10 additional times, right? So you have this kind of fractal pattern where we have this one go up 9 out of 10, no lightning, 1 out of 10 lightning. So we have to multiply these two numbers together to give us the 4 possible conditions. Okay, hopefully that made it a little bit more clear. It might not have. It's very difficult to kind of get the intuition for probabilities on the first time, right? But as long as you understand that we should multiply two probabilities when they are when they're not related in any way, right? We should multiply the two things. For example, I flip a coin, and draw a card. Okay, what is the probability I get a tails and a heart? Okay, so what's the probability I get a tails and a heart? Well, I flip a coin. What are the odds I get a tails? 1/2. So half the time, if I did this thousands of times, half the time I would get tails. The other half we don't care about because it's already failed our question. It already got heads. We don't care about what it gets in the cards, right? So you take total number of lots of attempts, right? So let's say we're doing the same thing over and over again. Half the time we're going to get tails. So this is the tails half. This is heads half. Half the time we don't care about it at all, right? We don't care. Once we get heads, we don't care what the card gets, right? Once we get heads, we don't care what the card gets because we can't be right. We can't give us a truth condition. The odds that it happens divided by the total, right? And then the tails, right? Once we have a tails, what are the odds we get a heart? Well, there's 4 suits of equal size. So if you get anything other than a heart, say this is a heart, this is diamonds, spades, clubs. These 3 quarters here don't matter. The only thing that matters is this. Okay, so what we did is we now have this little piece, and that's going to be equivalent to 1/8. Nope, not 1/18th. 1/8 of our total, right? Because this is one piece, two pieces, three pieces, four pieces, and then it's equivalent on the other side, 5, 6, 7, 8. Okay, so 1/8 is how we get, that's the number of chances that we get tails and a heart. So what we do is we take 1/2 times 1/4. We first break it into a half, and then we break that 1/2 into a fourth. Okay, that's kind of the basics of probability. Okay, hopefully this made probability a little bit more clear. And if you're still having a little bit of trouble kind of imagining this, go try out some more questions, right? There's also a couple other videos online that you might find helpful, or textbooks online that you might find helpful. But I definitely say use the ACT resources that we provide, just because they're super helpful. And I know they've helped a lot of students understand these same kind of concepts. Okay, let's keep going. Next thing we want to cover is trigonometry. Now, I wrote down trigonometry, but trig is a huge subject, right? There are entire classes dedicated to trigonometry, right? So it's going to be very difficult to cover all of trigonometry. I'm going to cover basically the basics and the things that I see the most often on the ACT that students get wrong. Okay, so the basics. Hopefully, we've all seen a right triangle before. Let me actually write down trig to keep it the theme. Trigonometry, kind of a long name, right? But either way, so we have a right triangle, and trig has to do basically with the ratios of the angles in a right triangle, okay, or in any triangle technically, but we care about a right triangle more, okay? So let's say we have a right triangle, okay, and let's say we have side length or angles A, B, and C. That means we have side lengths A, B, and C. Okay, so the side lengths across from the angle are the same letter. Okay. So the goal here is, well, let's just look at one of our angles to start. Let's just look at angle A. Okay. What we do is we label the sides according to what angle we care about. So let's say we care about angle A, and we're going to label each side. This side is going to be labeled as opposite. You've probably all seen this before. This one's going to be labeled as adjacent. This one's going to be labeled as hypotenuse. Okay, so the one opposite from the right angle is the hypotenuse. Okay, this might be basic, elementary for you. But let's actually get to what is the most important saying in trigonometry? Well, it's SOHCAHTOA. Probably seen this if you've taken trig before. What this is saying is, so, sine, the sine of some angle, we'll call it angle A, right? So that's this angle down here, right? Sine of angle A is equal to opposite over hypotenuse. So opposite over hypotenuse. Okay? So sine of A is opposite over hypotenuse. Cosine of A, the cosine of A is the ratio of the adjacent to the hypotenuse. Notice I use the word ratio because that's what all trigonometry is, right? Sines, cosines, and tangents are just ratios of side lengths based on the angle. And then tangent of A is OA. What do you think that's going to be? That's opposite over adjacent. One quick thing you also should know is that tangent of A is also equal to sine of A over cosine of A. This makes sense because if we were to take this and divide it by this, you would get this. Okay, so sine over cosine. Okay, so keep those things in the back of your mind. But these are the most important things in trig. You need to know these to get any kind of question, right? So let's say, real briefly, if I had a right triangle that looked like this, and I knew this angle was 30, and I wanted to find, and I knew this side length was, I don't know, say 3, and this is a right angle, and I wanted to find, let's say, the hypotenuse. So I wanted to find h here. How would I do it? Well, I know this angle, so relative to this angle, what is 3? Well, 3 is the opposite side, right? So we know the opposite, and we're looking for the hypotenuse. So which trig function links opposite and hypotenuse? Well, it's going to be sine. opposite and hypotenuse. So we could say sine of the angle 30 is equal to the opposite 3 divided by the hypotenuse h. And what we now have is one equation with one variable. So we can solve for h pretty simply, right? You can use a calculator, or you should probably know what sine of 30 is off the top of your head using a unit circle. If you haven't studied the unit circle in the past or you need a refresher, go look up a unit circle online. Okay, so that's the basics of trigonometry, right? Let's keep going with kind of the most important thing you see in trigonometry that students get wrong all the time. What that is graphing, zoom out here, graphing sine and cosine. The ACT loves to ask about graphing sine and cosine. Usually one question of test, at a minimum, is about sine and cosine and graphing them specifically. So let's talk about graphing. They go on a regular graph, just like you normally would, right? And they have a y-axis, just like normal, and an x-axis, okay? So they have a normal graph, and let's just start with sine really quickly. The basic sine function looks like this, okay? And it repeats forever, right? Sine's oscillating. And what happens to it is it essentially oscillates forever in both directions, so it would go down like this and up like this, right? But either way, right, what happens is it goes up, it starts at 0, and then goes up to 1, and then goes down to -1 and returns to 0. Now, how often does it do this? Well, it repeats the cycle every 2 pi. The x-axis is actually in radians here. Okay, 2 pi is also 360 degrees, but when graphing it, we like to use radians because radians represents the actual ratios of a circle, the lengths of a circle, a little bit better, right? So we like to use radians. So we go from up to 1 and down to -1, and then over from 0 to 2 pi, okay? So that's the basic function. Now, what that looks like is if I just graphed y equals sine of x. That's what this function is, okay? Now let's say I wanted to change it in some way, right? Or the question asks us, what does this change do? There's 4 ways you can change a sine function or a trig function. Okay? First of those ways is to change its amplitude. What that means is increase the height at which we go up to every rotation and the height at which we go down to, right? Something like this. So if I wanted to change it to red, right, that change would look like y equals a sine of x. And that a is the new amplitude. Basically, we go up to a and down to -a instead, okay? So the a is going to look like this red graph. So you basically multiply a by sine of x. That's the first major transformation you can make to sine and cosine functions, right? You increase the height at which the wave goes, okay? And you multiply by a. The second thing you can do is stretch the wave. Instead of vertically, stretch it horizontally, okay? And basically what that does is you're changing the period, okay? So normally we rotate every 2 pi, or repeat every 2 pi. But let's say we wanted to repeat every pi. So we want to go twice as fast. So in every 2 pi, it actually repeats twice. Okay? If we wanted to graph this, what we would do is we take y equals sine of 2x. We put the constant, instead of on the outside for a vertical stretch, we put it on the inside of the parentheses, right? Inside the sine function, okay? What this 2 means is whatever this constant is, every 2 pi on the graph, every 2 pi, how many intervals or how many full rotations or revolutions does this graph make, right? How many times does the wave cycle repeat over a period of 2 pi? Right? So in 2 pi, if we wanted to make it repeat twice or 3 times, you would just write a 2 or a 3, right? If, for example, we wanted to make it look like this instead, so it repeats twice as few times, right? It repeats half as often, we would put a 1/2 here, right? Because every 2 pi, we repeated half of a cycle, okay? So that's what the horizontal stretch can do for you. Okay. And then, so that's the blue function, right? Those are the options is blue. And then there's a third and fourth thing that we can also do. Let's look back at our base function. Okay. So the third thing we can do is shift the entire graph. Instead of stretching it, just shift the graph up or down. The way we do that is very simple. We take y equals sine of x and just add whatever we want our vertical shift to be, right? We'll call it c. If we want to go off by 1, so our graph looks like this instead, right? If we want to do that, we just c plus 1. You make c equal to 1, okay? If you want to go down, same thing, minus 1, okay? Then the last thing you can do is basically, instead of doing a vertical shift, you can do a horizontal shift. So instead of starting at 0 right here, say you just want to start this way, right? And how far over is that? Well, we know our total period is 2 pi, so this is a pi. So if we want to shift our starting point over by pi, what we can do is y equals sine of x minus our shift. Minus, we'll call it s, our shift. In this case, it would be minus pi. Now be careful. This is kind of counterintuitive, right? Usually we think when we go to the right, our x value is increasing, right? But here what we're doing is if we want to shift right, we're actually taking minus whatever our shift value is. We're subtracting whatever our shift value is, right? And if we wanted to go left or vice versa, right? If we want to go left and shift our thing left, right? We're actually going to have to do plus, 2 pi or something like that. If we want to shift our function left by 2 pi, right? Now, I should warn you that these are the 4 most important things with sine and cosine on a graph, right? It doesn't mean these are the only things that can happen, but really these are the only things that are going to show up on your ACT, okay? So these are the only things you really have to worry about at the moment. I should say the last thing, I just showed you a sine graph. Now, a cosine graph acts exactly the same, right? So a cosine graph, right? If you want to shift it vertically, you do plus c on the end, right? If you want to stretch it horizontally, you put a factor on the inside near the x. Same exact thing. But if I want to graph y equals cosine of x, right? We're going to have the same balance, 1 to negative 1, the same period, 2 pi, right? But instead of starting in the middle like this, right, we're actually going to start at 1 and start by going down and then coming back up. Okay, so a sine function would look like this, right? And a cosine function would start at 1, right? So basically, a cosine function is just a sine function shifted over by pi over 2, half of, or a quarter of 1 total shift, okay, or 1 total period. Okay, so hopefully that gave you a basic understanding of sine and cosine and tangent or sine cosine functions, right? Those are the biggest things in trig that you need to know. This is not all of the things in trigonometry you need to know. There's the law of cosines and the law of sines, which I'm not going to be able to cover for today, that are very important, right? There's Pythagorean theorem, which is related to trigonometry. There's the unit circle, the base 45, 45 degree 90 angles, 30, 60, 90 triangles, those kind of things, right? So definitely go review those on your own. If you didn't immediately recognize any of the things I just said, go read the trigonometry portion of the Ultimate Guide to the ACT Math section, okay? But this is the most confusing thing for many students. It's the thing that most students haven't learned in the past and show up very often, right? It's ubiquitous on all of the ACTs, okay? So now we're moving into our fourth kind of major topic, powers and logarithms. And for this one, it's kind of a lot of rules that we're just going to be listing out and talking about how to use, okay? So briefly, let's write out powers and logarithms. Powers and logarithms, okay. So what can I do with powers and logarithms? First of all, what is a power and a logarithm? Let's say a power is, well, say we take the number 3 and we take it to the power of 2. 3 squared. You've probably all seen this before. What that does is it just takes the base number and multiplies it by itself, multiplies it by itself however many times in the power. Right? So 3 to the 4th will be 3 times 3 times 3 times 3. 4 3's multiplied by each other. So that's how a power works. Now we can write the equation, say 3 squared equals 9. We all know this most of the time, right? Um, so 3 squared times 3 squared equals 9. What can we do with this information? Now, there's a useful thing called a log that lets us relate this power in a little bit of a different way that's a little bit easier to graph and useful for real world applications. Okay, so if I was to say 3 squared equals 9, there's another way I can write this equation. I could say log base of 3 of 9 gives me 2. Now, that might be a little bit confusing, right? But let's walk our way through this. What this bottom equation is saying, it's basically asking the question. A log asks the question, what power of the base, right? That would be 3, base 3. What power of the base gives me the value? Here in this question, right? It's asking what value of 3 gives me 9. What power of 3 gives me 9? And if we think about it like that, it becomes very easy to answer, right? What power of 3 gives me 9? Oh, it's 2. Okay, so if I asked you, right, to figure out log base 2 of 8, right, just think about it in that same format. What power of 2 gives me 8? Okay, how many times do I have to multiply 2 together to get 8? Well, 3 times. So log base 2 of 8 is 3. The other way we can write this, if we wanted to convert it to exponent form, we would write this as 2 to the power of 3 gives me 8. Okay, so this is the power form, and this is the log form. Okay, so that's the basics of logarithms. There's a couple of rules we want to discuss. First, let's talk about powers. Okay, what is a power? What can we do with powers? Let's say there's a lot of questions that ask us to simplify this, like 6x to the negative 3, y to the 4th, z squared, divided by, we'll say 9 x squared y to the negative 2 z to the, just z. Okay. How do we simplify something like this? And let's say we take it to the negative 2. Okay, how do we simplify something like this? First thing we do is work from the inside out. Work from inside the parentheses, right? If you remember PEMDAS, order of operations, you might have heard that before. We start with parentheses, then exponents, then multiplication and division, then addition and subtraction. So start inside the parentheses. Okay. How do we simplify this stuff? Here's the goal. We only simplify stuff that has the same base, right? So we can only care about, when we're looking at this y, we only care about other things that have a base of y, right? We don't want to care about the x's, okay? We don't combine them at least, right? So let's start with the whole numbers, 6 and 9. Can we simplify those? Yeah, sure. That simplifies to 2 and 3, right? So I've simplified, and we've already got open parentheses 2, in the numerator and 3 in the denominator, okay? Now, x to the negative 3 over x squared. How do we simplify that? Well, a trick with powers is if you ever have something to a negative power, right, like x to the negative 3, or let's say, we'll do numbers, like 4 to the negative 3, something like that. 4 to the negative 3, all that's saying is just fancy notation for 1 over 4 to the 3. Basically, if you take the stuff from the numerator and put it in the denominator and flip the power, the value stays the same. Okay, so a negative power literally just means the inverse of the positive power. Okay, so 1 over 4 to the 3 is the same thing as 4 to the negative 3. So what can we do with this x now? Well, x to the negative 3, that's the same thing as having x to the 3 in the denominator. So you just brought a negative power and made it positive in the denominator, just like that. Okay, so we now have x to the 3 in the denominator, and combining these two together down here, x squared and x cubed times x cubed is just x to the 5th. Right, so this is another one of the power rules, right? Another one of the power rules is x to the a times x to the b. If you have two things with the same base multiplied by each other, just add their powers together, right? This makes sense, right? 2 squared times 2 to the 3rd is just the same thing as 2 times 2, right? Times 2 times 2 times 2, which is just 1, 2, 3, 4, 5 2's added together, 2 to the 5th. So you add 2 plus 3. Okay, so that's power rule, another power rule that shows up. So what can we do with this? Well, now we've simplified the x's, and we do the same thing with the y's, right? We have y to the negative 2 in the denominator, y to the fourth in the numerator. So combine them in the numerator. We want to make positive powers, right? Y to the fourth times y squared, because we brought this negative 2 up to the numerator. That gives us y to the sixth, right? Y to the sixth. And then z to the first power and z squared. Well, how do we do this? Well, we want to simplify them somehow. We bring the smaller z to the bigger z. Basically, that means we're going to be left with z squared and z to the negative first. It works both ways, right? If we take a positive power and move it to the numerator, it'll give us a negative power. Z squared and z to the negative first. Combine these two, 2 plus negative 1 is just z to the first. Okay, so now what we've done is we've simplified all 6 variables into just 3, right? And we still have a power of negative 2. Now, what do we think this negative 2 is going to do? Well, it's doing the same thing we've done all along, right? We're going to flip it, and it's become a positive power. So instead, it's going to be 3x to the fifth divided by 2y to the sixth, z to the first, to the positive 2. Now, how do we do this? Well, squaring the whole thing, you literally just square each individual term. 3 squared is 9. X to the fifth squared is x to the 10th. What that does is whenever you have a nested powers like this, right? One power to raise to another power, you just multiply them together. 5 times 2 is 10. So you get x to the 10th in the numerator. Divided by 2 squared is 4. Y to the 6th squared is y to the 12th. And z to the first squared is z to the second. So this is going to be our fully simplified version of this thing at the beginning. Okay, so that's one of the big, power rules that show up a lot on the ACT. Okay, so make sure you know how to do those. The last thing that comes up with logs and powers like this, right, is log. Let's say we have log base 2 of 8, right, equals 3. Actually, there's a better way. There's a couple of rules. First of all, let's say, I'll just write the rules down. Say log. Okay, so that's all we'll cover with powers and logarithms. There are a couple of rules. They're all can be found on the math formula sheet, so definitely go check out the rules on logs in the math formula sheet. And if you're confused by how any of them work or why any of them work and want to investigate, go check out the Ultimate ACT Guide, like I've been saying the whole time. Right? But now we're going to move into our last kind of topic. Our last topic here being complex numbers and matrices. Okay, so complex numbers and matrices, these are the pre-calc topics that show up a lot, right? And a lot of students haven't covered pre-calc yet when they take the ACT, so they need a little bit of a review to figure out how to do these. Right? So matrices plus complex numbers. I can't cover everything with either of these two subjects, but I can cover the basics. Matrices. The biggest ways they show up are, well, briefly what a matrix is if you don't really know. It's just a set of numbers in a grid that represents a system of equations, specifically the coefficients of a system of equations. That's not super important. We don't really care about that for the ACT. What we care about is what it looks like. For example, 2, 6, -1, 0. That can be a matrix, right? Now, all of the ACT questions are going to be based around either multiplying matrices, adding matrices, or multiplying by a constant. 3 things. So the easiest of these is multiplying by a constant. If it asks you to do 5 times a matrix, or any constant times a matrix, you just do 5 times each individual component of the matrix, giving you 10, 30, -5, and 0. Right? So that's pretty simple. Okay. Now let's say they wanted us to add 2 matrices together, or subtract 2 matrices. In order to do that, there's a couple of requirements. First, the matrices must be the same size, right? I can't add a 2 by 2 matrix plus a 3 or a 2 by 3 matrix like this. 2, 3, 4, -1, 0, 6. I can't add these together because they don't have the same size. The reason for that is we need to be able to add the matrices component-wise. Basically, add the top left corners together, add the bottom right corners together, and so on. This is going to give us a 2 by 2 matrix. 2 plus 3 is 5. 6 plus 4 is 10. 2 plus 5 is 9. 9 plus 3 is 12. 12 plus 4 is 16. 16 plus 4 is 24. 24 plus 5 is 28. 28 plus 4 is 32. 32 plus 4 is 36. 36 plus 4 is 48. 48 plus 5 is 49. 49 plus 6 is 51. 51 plus 4 is 49. 49 plus 6 is 51. 51 plus 4 is 51. 51 plus 6 is 51. 51 plus 7 is 51. 51 plus 8 is 51. 51 plus 9 is 51. 51 plus 10 is 51. 51 plus 11 is 51. 51 plus 12 is 51. 51 plus 13 is 51. 51 plus 14 is 51. 51 plus 15 is 51. 51 plus 16 is 51. 51 plus 17 is 51. 51 plus 18 is 51. 51 plus 19 is 51. 51 plus 20 is 51. 51 plus 21 is 51. 51 plus 22 is 51. 51 plus 23 is 51. 51 plus 24 is Negative 1 plus 2 is 1. 0 plus negative 1 is negative 1. And the same thing would work with subtraction. 2 minus 3 is negative 1, and so on. Okay, so these are pretty simple with matrices. There is one topic that shows up on the ACT that you should know for matrices that's a little bit more difficult, and that's multiplying two matrices together. Okay, so a little bit of background. Let's say we're multiplying 2, 3, 4, 0 times 1, 6, 2, 7. The requirement to multiply matrices together is not that they are the same size. I'll show you what actually matters. We label the size of a matrix as the row number by the column number. So in this case, it's 2 rows by 2 columns in each of them. So each one would be size 2 times 2. What matters for matrices when we multiply them is we're only able to multiply them if, when I write 2 by 2 by 2 by 2, we need the columns of the first one we multiply to be equal to the rows of the second. So we need these two numbers to be equal. Okay. Now let me show you why that's the case. We don't actually have to multiply matrices together on the ACT. We do have to know this rule. For example, if I was to multiply 1, 2, 3 rows by columns by 1, 2, 3, we could do this because this one's size on the left is 3 by 1, and this one's on the right is 1 by 3, right? So these have the same column and row, right? And their actual size, the size of this product, is going to be the outside pieces, 3 by 3. So if I multiply these two matrices together, I get a 3 by 3 matrix. The reason for that has to do with, with a little bit more, complex pre-calculus and linear algebra. But to know for the ACT, all you have to know is matrices are sized by their rows and columns, right? So row by column, that's how we label the size of a matrix. To multiply two matrices together, you better make sure that the columns of the first match the rows of the second. Okay? They have to be the same size. Always be careful. Okay? So that's it for matrices. The last thing I do want to cover in today's video, we're coming here to the end, are complex numbers. Okay? So what is a complex number? You might have not heard of it before. Okay? The thing we need to know first is imaginary numbers. Imaginary numbers. You might be thinking, what the heck is an imaginary number? That doesn't even make any sense. How that could be a number be imaginary, right? Well, I'll show you. We call an imaginary number I if I is equal to the square root of negative 1. That might be intriguing to you. Think about it. What is the square root of negative 1? I know what the square root of 4 is. It's 2. I know what the square root of 1 is. It's 1. What's the square root of 0? 0. What's the square root of negative 1? It's not negative 1 times negative 1, because negative 1 squared is negative 1 times negative 1, which is positive 1. So how do we multiply two numbers together to get us a negative 1? Well, we can't. We can't multiply any two real numbers together to get us a negative value, right? So an imaginary number basically fills in this gap in our mathematics, right? So we say I is the square root of negative 1. A complex number is a number, any number, that contains both real and imaginary parts. Real part, like an example of this, is 3 plus 2i, right? We have a real part and an imaginary part. This is called a complex number because it's complex because it combines real and imaginary. Okay, so this is a complex number. There's a couple of things we want to talk about. First is the complex plane. The complex plane is just a fancy way of saying a coordinate plane with real and imaginary parts. You know, on a normal coordinate plane, you have x and y, like on a graph like this. But what we have in a complex plane, right, is actually a real part. So we put the real part here and an imaginary part up here. So the y-axis is an imaginary axis now. So for example, if I wanted to graph 3 plus 2i, what I would do is I would look at the real part. What is its value? Well, I'd go over 1, 2, 3 in the real direction, and 2i, positive 2i in the imaginary direction, 1, 2. So this would be our complex number. Technically, it's defined as a vector, so it would look like this. But for the ACT's purposes, just know that this is the point we care about when we say 2 plus 3i. It's the same thing as 3 comma 2 on a regular coordinate plane. Okay, so don't be tripped up. It's not too, complex here. Well, no pun intended. But, be careful when we're doing something like this. Okay. So the last thing I want to talk about with imaginary numbers is the pattern that I has, and specifically when it's multiplied by itself. Okay. Um, so this shows up a lot. Say a question is asking, what is I to the 271st? No, we'll do 273rd. What is I to the 273rd? Well, I to the 273rd is just I multiplied by itself 273 times. But I times I, well, I is the square root of negative 1. Okay, fair enough. I times I is the square root of negative 1 times the square root of negative 1. So I can say I is equal to I. I squared is equal to, well, what's the square root of negative 1 times the square root of negative 1? Well, that's just going to give you negative 1, right? Because the square root of negative 1 squared, the square of any square root is just the value itself. So the square and the square root cancel. So I squared is negative 1. What's I cubed? Well, I cubed is just I squared. I cubed is equal to I squared times I. So I squared, we just said, is negative 1, right? And so it's just negative 1 times I. So I cubed is just negative I, right? So we figured this out pretty easily. And I to the fourth, well, what is I to the fourth? Well, I to the fourth is just I squared, right, times I squared, right? So what's I squared? Well, I squared is negative 1. So that's just negative 1 times negative 1, which is just positive 1, right? So I to the fourth is really just a positive 1, okay? And then what is I to the fifth? This is the last thing, I to the fifth. This is the farthest we'll go, I to the fifth. Well, I to the fifth is just I to the fourth times I to the first, right? Oops. I should probably zoom in here so you can see it. There we go. So I to the fifth is just I to the fourth times I to the first, which is just, well, we just said I to the fourth is just 1. So it's just 1 times I, which is just I. So I to the fifth in reality is just I, right? So now what I've shown you is I've shown you a progression of all these numbers, of these imaginary numbers, right? A progression that is the same, it's constant, right? And it repeats itself, right? We see I to the first is just I, and I to the fifth is just I. So it will repeat the same 4-pattern cycle over and over and over again forever for an infinite number of I powers. We can use this to our advantage, and this kind of technique shows up on the ACT a ton, not just with imaginary numbers, so pay attention, right? If we have I, imaginary numbers, right, or if we're looking for I to the 273rd, right, and we wanted to figure it out, here's what we do. All we have to do is figure out where 273 is in this pattern of 1, 2, 3, and 4 powers, right? Because if we can figure it out, if we say it's the second one, right, we can just match it to the 2 and we can get our answer of negative 1. So here's what we do, right? 273, we take 273 and we divide it by 4. Because if we divide it by 4, whatever we get as a remainder, right, whatever we get as a remainder is going to give us um, the location in this pattern, right? So the location, well, let's figure out what the remainder is first. 27 goes into 4, well, 6 times 4 is 24, minus, you get 3, dropping down to 3, 68, 8 times 4 is 32, give me a 1. It's going to give me a remainder of 1, meaning we're at the first position in our progression from powers of 1 to 4. Okay, hopefully that makes a little bit of sense. What that means is I to the 273rd is just equal to the I to the first value, which is just I, or the square root of negative 1, whichever one the answer choice wants us to give, right? So I to the 273rd, without doing a whole lot of math, just some long division, right? Once we know this, right, just some long division, we can figure out, oh, I to the 273rd, right, is just I, which, that's it, or I to the first, which is just I. Okay? This same kind of progression shows up all the time, right? And you should recognize it if you can find a pattern in the powers, right? If you can find a pattern in the powers, you take this long division and its remainder gives you the location in that pattern. Okay. Okay, so that's going to be it for today's video, right? So these are the 5 subjects that we kind of covered. Now, I should say once again that this is not a comprehensive review, right? This will not teach you everything you need to know for the ACT. However, if you struggled with any of these topics beforehand, or you were a little bit confused by any of the things when I first said them, go back and rewatch this video a second time, right? And go review questions related to them in the ultimate guide to the ACT, right? Um, on our IP tutoring resources. Okay, so that's going to be it for today's video. Remember, our next video is going to be focusing on how to we're going to go through a math test. Basically, we're going to go through start to finish, or as many questions as we can get through. I'll show you how to do all the questions, right? So it's going to cover a little bit more broad content, right? But I'm not going to be able to promise that it will cover everything, but you'll be able to get to see some of these tips and tricks in action, plus some other concepts you might need some help with. Okay, so I hope to see you in that next video. Thanks for coming to lesson 4, and I will see you next time you check in. Bye now.